This is our first video on dynamics, and its introduction to forces and Newton's law. So force is another vector quantity or the vector variable that we're going to be looking for or solving for. And force is measured in newtons. So you can see the force is measured in newtons. And so Newton's laws, 3 Newton's laws. The first one is about inertia. So it states that an object will remain at rest or move with a constant velocity when there is no force acting on it. And you can imagine if somebody in space far away from any planet kicks a pebble, that pebble or that rock will be flying without changing its velocity or direction until the force acting on it. In order for an object to stop its motion, you have to apply the force, or in order for the object to accelerate or change its velocity, you have to apply the force. So the first law says that if there is no net force acting on the object will be doing what it is doing. So if it's moving at a constant speed, it will keep moving at a constant speed. If it is not moving, it will not be moving. And inertia is the resistance to change. So another word for inertia is the laziness. So you are sitting on the chair, and in order for you to change the state, you have to apply the force. So you have inertia, like you don't want to change what you're doing until the force is applied. It is proportional to the mass. Inertia is proportional to the mass, and the bigger masses resist the change in their motion more than the smaller masses. So the bigger mass, the more difficult it is to change its velocity. So let's say you have a bicycle and you have a truck, and you want to change their velocities. The truck has more mass, so you have to apply more force in order to change its velocity. And the bicycle is smaller, you have to apply less force to change its velocity. So the bicycle is less lazy than the truck. For the second Newton's law, he did not state the way it is written here in our description here in the lesson, and I'll show you in a second how he stated it. But he said, if the net force acting on an object, so if there is a present net force, and the net force is the sum of all the forces acting on the object. So if the mule, do you remember the mule problem? We had mule being pulled by one person in one direction, the other person in the other direction, and then they would be the resultant force. So that resultant force would be the net force. So if the net force is acting on the object and is not zero, then the object will accelerate at the direction of the exerted force. And what he wrote is this. He said, if you apply a force for some amount of time, then your mass will have change of the velocity. And the way it's written now is the force is equal to the mass change of the velocity over time. In other words, the force is equal to mass times acceleration. So that's how he wrote it first. So this is the way he stated his second law, but we look at it as it is written in the lesson now. And then for the third law, you heard it many times. So whenever one object applies the force on the second object applies the force on the first object. That is equivalent in magnitude but opposite in direction. In other words, for every action there is equal and opposite reaction. So these are the 3 Newton's laws, and we're going to be solving questions related to these laws and do the Freebody diagram. Freebody diagram is where we have to write all the forces present, and we'll always use the second Newton's laws to find acceleration. And then kinematics is going to be involved in lesson solving as well. So the forces that we do need to know. So when you're sitting right now on the chair, you are not flying away from the chair because the force of gravity pulling you down, but then the chair pushing back at you because you push on the chair and the chair pushes back at you with exactly the same force, Newton's third law. So what we are experiencing is the force of gravity, and the resultant force is the normal force. The normal force is always going to be perpendicular to the surface. So that is a specific rule about the normal force, and that's what it's called normal. Normal means perpendicular. So the force of gravity has the formula. The force of gravity is equal to mg. G is acceleration due to gravity. The actual force of gravity, the force of attraction between two objects, it has a different formula, but for now we're going to look at the force of gravity is equal to mg. The normal force doesn't have a formula. It changes all the time depending on the circumstances. So we're going to derive the normal formula for the normal force formula every time we solve a problem. Then let's say you have an incline, and on that incline you have book sliding down. So if the book is sliding down because the force of gravity is acting on it, so you would have the force of gravity, and when the book is sliding, there is going to be a force of friction, the one that is slowing down the book from sliding. And the force of friction is always opposing the motion. So if you move forward, the force of friction is going to be back to the back. And the force of friction has its own formula as well. It is mu times n. N is the normal force. So n would be this force. That would be your n, the one that is perpendicular. So the book is pushing on the table or the plank, and the plank is pushing back on the book. So that's the normal force, and as always it is perpendicular. And mu is the coefficient of friction. So this mu, you write it like this. It's almost like u and then little tail in front. So that's mu, mu, mu. And this is the coefficient of friction, and it is dependent only on the materials that are in contact. So there are tables, and here I found you one of these tables. So let's say you can see that the wood on wood will cause or will have coefficient of static friction. I'm going to talk the difference between them: static friction or kinetic friction. And let's say ice on ice. If you have an ice of something sliding on ice, you will have coefficient of friction, static and kinetic. Then metal on metal is going to have a different coefficient of friction. Do you see that it doesn't depend on anything but only on the material? So let's say you have the rubber on the dry concrete, you will have coefficient of friction and kinetic coefficient of friction. So Teflon on Teflon in air, and Teflon on steel in air. So they will have different coefficient of frictions, and all it depends on is the material that is in contact. Now, what's the difference between kinetic friction and static friction? Let's say you have two books. One is made of one material, and the other one is made of a different material. Maybe one is carton board and the other one is just paper. And you have them both placed. When you reach an angle of your plank under a certain angle with a horizontal, one book starts sliding. Let's say this one is started sliding, starts having some velocity, and the other one is not sliding yet. So the one that is not sliding yet, what holds it is static friction. So this one would be static friction. I'm going to say Fr for friction, and here will be mu static times the normal force, and the normal is perpendicular, right? And there is force of gravity, mg. But for the second one, the one that is sliding, it has friction, but this one is the kinetic friction because it is moving, sliding. So this would have mu kinetic times the normal force, and this would be the normal force for the second book, the one that is sliding. So kinetic is when it is sliding, and static is when it is not moving. So what holds it is the force of friction, but there is no sliding happening yet. So my question is this: when you walk on the ground, is it static friction that holds you on the ground, or kinetic friction? Or when the car is driving on the street, is it static friction or kinetic friction? And when you think about this question, and I hope you have an answer in your head, right or wrong, but you have an answer. So when you think about it, when you walk, do you slide or do you walk without sliding? So if you walk without sliding, that means what's holding you on the ground is the static friction. And when the car is driving on the ground, unless it is skidding on the concrete, then that one is also called static friction because it's not sliding on the ground. So this is the difference between static and kinetic friction, and they have different mu, coefficient of friction, for static and kinetic. So far, this is what we looked at. We looked at the normal force. We have the normal force, the one that's perpendicular to the ground. We have the force of gravity, mg. So this would be mg. This would be the normal force. You could apply force. So I'm going to call the force to the right applied force. And there would be a friction force, and that would be the kinetic friction, because in this case, the box is sliding. So these are the few forces that we're going to be looking at right now. And also you have to know that the static friction is larger than the kinetic friction, just because it is. So let's look at some of the questions, how to solve them. So in this first question that we're going to look at, we have two people, A and B, are dragging a canoe out of a lake into a beach using light ropes. Each person applies a force of 60 newtons on the rope. The force of friction exerted by the beach on the canoe is 85 newtons. So the friction is given 85 newtons. So I'm going to put the friction force right away. So the friction and this, the kinetic friction, right? So the friction is there, and it is 85 newtons. 85 newtons. Each person is exerting a force of 60 newtons. So this one is 60 newtons, and this one is 60 newtons. And person A thinks that if A and B each pull the rope, forming an angle of 20 degrees with a bow, so each one is 20 degrees. So you have theta, and you have theta, each 20 degrees. The net force on the canoe will be greater if they pull straight parallel to each other. The canoe is being dragged along the beach using the ropes that are parallel to the surface of the beach. Starting with the Freebody diagram, calculate the net force on the canoe if person A thinking correct or not. And then for the second part, they ask you, we're going to do the second one. Let's cover the two first and then do the question that they ask. So I have the forces. I have this force 60, this force 60. The angle between them is 40 because each makes 20 degrees with the middle part. And then I have the force of friction, which is 85 newtons. Free-body diagram. What is this? For the free-body diagram, I have to again complete the parallelogram to find the resultant force. So your free-body diagram shows the forces. Your resultant force is going to be this force, and I'm going to call it F. And I want to mention that this was 60 newtons and this was 60 newtons. What I have is 40 degrees here and 40 degrees here. That makes 80. And a parallelogram has 360. So what's left is 280 degrees. That means that each of these angle is 140. So this angle is 140 degrees. I'm going to use this green triangle to find the resultant. I see that I have a side 60, another side 60 because it's a parallelogram, so it's the same as the other side, parallel to it, and angle of 140. I have side angle side. So when I have side angle side, I use the law of cosine. So I'm gonna say, and I'm looking for the f, right? So my f is equal to f squared is equal to 60 squared plus another 60 squared, one side plus the other side, minus times 2 those sides, so that's 60 times 60, 3600. And then cosine, the angle between them is 140 degrees. So F is equal to the resultant force, 112.8 newtons. So the resultant force is 112.8 newtons. But that's the force that the men are pulling. That is not actually the net force. The net force is the sum of all the forces. So the net force in this case is going to be 112.8 minus 85. which is 27.8 newtons. So this is my net force. And the man was saying that they should pull under an angle. If they did put on it with an angle of 20 degrees, if they would just pull it straight to the right, then we would have 120 degrees as your net force, the net force between two men, right? The resultant force for two men would be 120, not 112. So I don't think the man, the person A, was right about it. They would have stronger pulling force if they were pulling to the right together. And for number 2, they tell you, I'm not going to erase this, I don't want to mess it up, but number 2 tells you if the boat started, this was number 1 question, right? Number 2 says if the boat started from rest, so I know initial velocity is 0. If the boat started from rest and has a mass, so the mass of the boat is 300 kilograms, what will be its velocity? And m is the mass, right? In the formula that we saw in Newton's second law, m times a. Mass is going to be measured in kilograms always. So, and the mass of the canoe is 300 kilograms. What will be its velocity in 10 seconds? So time is 10 seconds. So this is given for the second question, number 2. So I can figure out, at first I'm going to figure out the acceleration. So I know that the net force is equal to mass times acceleration, Newton's second law. The net force that I calculated is 27.8. The mass is 300 kilograms, and I can find acceleration of this canoe. So acceleration of the canoe is equal to 0.093 meters per second squared. So I got my acceleration. And the next question is, what is going to be the velocity of the canoe in 10 seconds? So the final velocity of the canoe is equal to initial velocity plus the acceleration times the time. Acceleration is initial velocity is 0, right? So I don't have to write that one. Acceleration 0.093 times 10 seconds gives you 0.93 meters per second. And then there is the third question that is asking you how far did the canoe move into the shore in these 10 seconds. So we did the second question right now, and let's look at the third one. So they ask you the distance it moved over these 10 seconds. It's the average velocity times the time. Initial velocity is 0, final velocity is 0.93, divide by 2, and the time is 10 seconds. So that looks like it's going to be 4.65 meters. Let's do another question. These are the most simple questions that we will do in our dynamics problem solving. So a store sign that experiences a downward gravitational force of 245 newtons is suspended as shown. Calculate the force tension 1 and tension 2 exerted at the point at which the sign is suspended. So what's given is the force of gravity. The force of gravity is 245 newtons. So this is 245 newtons. And then you have tension 1. So here is tension 1. So I'm going to call this one is tension 1. And this one is tension 2. And I cannot use the forces that are off my x and y coordinates, because I'm always going to look at the accelerations on x and y. So here I need to project or make a components for the horizontal and vertical forces. So my T2 aligns with x. My force of gravity, 245 newtons, aligns with y, but my T1 is off the course. It's with an angle. So I'm gonna make the right triangle right here, and I will have to make horizontal and vertical component of that vector. And since this angle is 55, so will be this angle 55, because there is this line that is parallel to this line. So if I draw my forces, so this is my horizontal component, this is my vertical component, and my vertical component is opposite of the angle, so that is T1 sine theta. You see how often we use this? And my horizontal component is, or I can call it Ty and Tx. So my horizontal component is Tx, and that one is adjacent to the angle, so that is T1 cosine theta, and my theta is 55 degrees. So now I have to do my Newton's second law for horizontal and vertical forces, because in this case your net force, not net forces, or net force is equal to 0, because the object is not accelerating left or right or moving at all. So the forces are canceling each other, so the net force is going to be equal to 0. But I'm going to do the net forces on x and the net forces on y. And what I'm using is F net is equal to ma, but because there is no acceleration, I can write equals to 0 because the acceleration is not present either on x-axis or y-axis. So for x-axis, I have, and I'm going to choose the direction to the right to be positive, direction to the left to be negative. On x-axis, I have T2 in the positive direction, so T2 is positive, so I'm looking at the net force first, and then m8 on the other side. So I have T2 to the right, but T1 cosine to the left. So that one is negative because it's to the left. T1 cosine theta, and it's up to you which direction you're going to choose, positive or negative. And because there is no acceleration, I could write mass times acceleration. Oh, by the way, what is the mass? They give you mg is equal to 245. So that is mg, right? The force of gravity. And g is 10. So what is the mass? I hope I hear 24.5 kilogram. So they give you the weight of the box. They don't give you the mass of the box, and the mass is 24.5 kilogram. So in this case, your acceleration is equal to 0, so your ma is equal to 0. Now on the y-axis, I have two forces as well. One is pointing up, which is T2 sine, and the other one is pointing down, 245 newtons. So I'm going to choose my direction, and it's up to you what direction you want to choose, positive, it doesn't matter. So my direction, positive, is going to be up. Then I have T1 sine theta, and mg is negative, so minus mg. And again, it's equals to 0 because there is no acceleration in this case. So now I can solve for T1 first. So I'm going to solve for T1 first. My T1 is equal to, which is easy, mg divided by sine 55. So I get mg 245 divided by sine 55 equals to 299 newtons. And then now, since I know T1, I can use the first equation, solving system of equations, Like I mentioned earlier, it's very important for AP Physics, solving system of equations. So I'm going to plug in T1 into my first equation and solve for T2. So T2 is equal to T1 cosine theta and equals to 299 cosine of 55. So T2 is equal to 171.5 newtons. I have 5.5 minutes left, so let's see if I can squeeze this one or two questions more. Easy ones. A person in an elevator have a combined mass of, mass is given, so let's write where it's given. Mass is, it's 610 to the second kilogram. And elevator cable exerts a force of, so elevator force is 6.5 10 to the third newtons. I have to fix it in the lessons. Upward, and the elevator find the acceleration. So let's look at the problem. So here is an elevator. The downward force is mg, and mg is equal to 6,000 newtons. They give me the mass, and g is 10. So, and the force that elevator exerts upward is on the cable is 6,500 newtons. So there will be acceleration. When they say free body diagram, they mean forces. So I put the forces, my red forces, but A is acceleration, it's not the force. So every time on AP exam they say draw the free body diagram, I just drew free body diagram, but my A should not be included into my free body diagram. So for here I have the net force, always net force. The net force is equal to ma, so always Newton's second law. The net force consists of two forces, one up and one down. So I'm going to use the up positive direction. So I have 6,500 up minus a negative one is 6,000 and equals to the mass, which is 600, and acceleration. So the mass is 600. I can divide by 100 all of them right away. So what's left is 5 is equal to 6a. So the acceleration is 5/6 meters per second squared. I'm gonna add an additional question to this question because I don't have time to go over the rest of the questions. So I'm gonna just add. So if the person is standing here, so if the person is standing inside of the elevator, so here he is. Let's say the person's mass, I'm going to say the person's mass, I'm going to P for person. The person's mass is 50 kilogram. As he is rising up, what is going to be the scale if there was a scale showing? So if he is not moving in an elevator, the scale will show 500 newtons, right? Because if he is pushing on the ground with 500 newtons mg, then the scale is pushing on him, Newton's third law, with 500 newtons. But because there is acceleration, you know that inside of the elevator, when you're accelerating upward, you feel heavier. So what I'm gonna look at it is this way. So if the person is standing, the forces acting on the person is mg, the mass of the person. The forces acting on the person is normal force, and that's the force that is the scale would be showing, the normal force. And then you have acceleration, and my acceleration is not the force. Again, I don't want it to be the same color. And then I'm going to write the Newton's laws for this question. I want to find out what the scale is going to be showing. So again, my F net is equal to ma. The normal force minus mg, that's my net. The normal is up, mg is negative, equals to a is positive, so a is going to be positive in this case. Sometimes a will be downward, and if I chose the direction to be downward, that is going to be negative. So the normal force is the scale, what is showing is the normal force is mg plus ma, and I just found my acceleration. So the normal force is equal to mass g plus a. And if I do my calculations, normal force is equal to, I have 50, and then I have 10 plus 5.6, right? 0.83, I believe, 5.6. So my normal force is equal to, in newtons, I got 542 newtons. So normally the person whose mass is 50 kilogram would weight mg, would be 500 newtons. So the person would weigh downward on Earth with 500 newtons, and the Earth would push back on him with 500 newtons. But because there is acceleration, because we have acceleration, the person will push on the scale more than 500 newtons. The person will push with 545 newtons, and the scale will push on him with 545 newtons. And it's all about the Newton's second law. And that is it for today's question. So this was just introduction for Newton's first and second and third law, and we're going to do more practices. These were the easiest ones.